Ah, welcome back. I know last week was challenging, learning about the concept of momentum and impulse, and it didn't quite click for a lot of people, but hopefully, with enough time, rewatching the videos, doing of Khan Academies, asking help, and seeking answers to your questions, hopefully it did start to click and we can actually kind of build some momentum here. Because ultimately, the reason we study momentum is to go ahead and study this concept of collisions. Collisions are entirely based within the laws of physics. Whether you have a car accident, the accident, the way the cars move has to adhere to the law of conservation of momentum. You don't know what that is yet, but that's okay. Billiards is a highly mathematical game, pool, and you've probably studied the angles and the vectors, but you have to understand that because the objects are of equal mass, that will affect the way the momentum is transferred with each other when they collide. And another thing that people don't necessarily think about is that when you are playing sports like football and you collide with another person, the person with the more momentum wins the collision. And you will see how that works shortly. The law of conservation of momentum. Like all laws of conservation, they simply mean that the total momentum of a system is conserved. By the way, momentum is singular, momenta is plural. Just a little Latin lesson for you there. So the total momenta of a system is conserved, meaning that when there are not other friction. Wow. Okay, sorry. When there's not friction or outside forces. I don't know what I was doing right there. When no friction or outside forces, the total momentum remains unchanged. Kind of like conservation of mass when you did chemistry, the total number of atoms in a chemical reaction stayed the same. When we did conservation of energy last year, where we transferred back and forth between potential and kinetic energy, it didn't matter how much you had because the total energy stayed the same. Here, the total momentum is going to remain unchanged. So when I say of a system, the total momentum of a system, what I'm really referring to is like if you're watching two things colliding, that's going to be your system. Surely other things can factor in. So like if you get in a car accident, you hit another car, there's a collision, but then your tires have friction on the road, then you might hit something else. Momentum is still conserved in all these ways. It's transferring to other objects, and we're going to see how that's going to work shortly. So again, the momentum of individual objects may change, but when added, the total momentum before the collision will equal the total momentum after the collision. So your momentum could still change with impulse, but in the essence of the collision, all you're doing is transferring the momentum back and forth between the two objects. So this is the total or sum of the momentum before is going to equal the sum of momentum after. So, law of conservation of momentum. I want to be very clear. We're going to get some new variables. A 1,000-kilogram cannon is initially at rest and then fires a 10-kilogram cannonball 100 meters per second. How fast does the cannon recoil? So let's think about this. How is this even like a collision? Well, you have two objects together and you have two objects apart. It's like the opposite of a collision, but it still must apply. The law of conservation of momentum must still apply. So let's think about it. We have two objects. We have a cannon and we have a cannonball. So let's call mass 1 the cannon, and let's call mass 2 the cannonball. Before anything happened, they were all at rest. So that means this velocity and this velocity were 0. Again, so the momentum before anything happened was 0. That means the sum of the momentum after the reaction must also be 0. But wait a minute, Pizzuto, how can it be 0 after the reaction if they're moving? Because they're moving in opposite directions. I think the directionality may have thrown some people last week with impulse and momentum, but directionality is critical. When the cannon has the recoil, the cannonball goes right, the cannon goes left. So let's see mathematically how this is going to work. When I said the sum of momentum, mv is just the equation for momentum, so I'm adding the momentum of the cannon to the momentum of the cannonball, and it's going to equal the momentum of the cannon plus the momentum of the cannonball. But what is this v prime? V with the apostrophe thing. This is called v prime. So what we have is we have v naught, and now we have v prime. And v prime is the velocity after an interaction, whether it be a collision or a situation like this. If you think about it as the velocity after something happens. V prime, okay? So it's almost like v and v naught, but momentum doesn't use v and v naught. Momentum uses v and v prime, but it's the same concept. So let's see how this works. So all I'm saying is that the momentum of the cannon plus the momentum of the cannonball has to equal the momentum of the cannon plus the momentum of the cannonball, before and after. That is all I'm saying. These primes shouldn't be there. Curses. Ooh, I'm failing today. So the mass times velocity of the cannon plus the mass times velocity of the cannonball equals the mass times velocity prime of the cannon plus the mass times velocity of the cannonball. So let's mathematically, let's actually do this. I'm just adding up all the individual momenta. If this object broke apart into 3 pieces, I would have 3 MVs. So I don't want you to get stuck into the idea that this is the equation. Just add up all the momenta before and all the momenta after, and they have to equal. All right? So, interesting things like, for example, a firework. A firework actually has to adhere to the law of conservation of momentum. It's going up in the sky, and when it explodes, all its pieces go every which direction. If you added up the momentum of all those pieces, it would be the same as the momentum it had before it exploded. So, the mass times velocity of the cannon, 1,000 times 0, because it started off at rest, plus the mass times velocity of the cannonball, also 0, because it started off at rest, equals the mass times velocity of the cannon. So we know the mass isn't going to change, but we don't know how fast the cannon's going, but we know that the cannonball is going 100. So I can just use algebra and solve that. I know that the cannonball is going -1. I knew it had to be negative, because if the cannonball was going right, the cannon had to be going left. And I knew that when I multiplied 10 times 100, got 1,000, subtract it from both sides, divide, there you go. Keeping it simple. All you're doing is you're adding all the momentum before, you're adding all the momentum after, and they have to be the same. This is why we did impulse last week, so you could recognize if there was a change. So, there are 3 types of collisions that can occur, and we're going to get into all 3 today. Elastic collisions. When 2 objects are moving, collide, and they continue moving separately after the collision. You're going to see examples of all these, but I just want to have one spot where I clearly define the 3 collisions. 2, totally elastic. It's a specific type of elastic collision where all momentum in a system is transferred from one object to another. So number 2 is really just like a special example of number 1. It really shouldn't be a separate type, but I made it a separate type just so we understand that these are the only 3 types of collisions that we're going to see. And then an inelastic collision, when objects collide, bind together, and move as one object afterwards. You may not be able to visualize any of this, but I've got gifts for you. So, I said the definition of an elastic collision is when objects are moving, and then they collide, and then after the collision, objects are moving. So these are 2 examples of elastic collisions. If you look at the very first example, the car is moving and the truck starts off at rest. They collide, and then both the car and the truck move. Awesome. Elastic. Because you have multiple objects moving before and after the collision, and or after the collision. The same deal with the other one. I don't want you to feel that in elastic collision they have to bounce away from each other. When the truck hits the car, this is another example of elastic collision because they're both moving after the collision, but in this case they're both still moving in the same direction. Most of the momentum got transferred to the car and the truck slowed down. Examples of elastic collisions. So, a 3 kilogram rubber ball rolling 4 meters per second collides with a 5 kilogram softball rolling -1 meter per second. Sorry, negative, just got put in the wrong line. If after the elastic collision, the softball is rolling +2 meters per second, how fast is the rubber ball rolling after the collision? Okay, well, we have two objects, a rubber ball and a softball. So let's see what we got here. I know that the total momentum before has to equal the total momentum after. So we can call the first object the rubber ball and the second object the softball. And we can just plug in what we know. So the mass times velocity of the rubber ball plus the mass times velocity of the softball equals the mass times final velocity, or v prime, of the rubber ball plus mass times v prime of the softball. Simple. It's just a simple equation. We have two objects moving before, so now we're going to have two objects moving after. That's the essence of an elastic collision. The rubber ball was 3, it was going 4. The softball had a mass of 5, it was going -1. If after the elastic collision, so after indicates prime, the softball, now the mass of the softball is going to stay the same. So the softball is still going to say 5, is rolling +2. How fast is the rubber ball, which is mass is not going to change either, rolling? So we're looking for the v prime of the rubber ball. Just use algebra. That's it. Don't make this harder than it needs to be. Okay, so this is an example problem that is going to have you, we're going to do some more trophies. I like the trophies. I think they're great. I really do. But I want to make sure that you understand them. So let's go ahead and look at this. It says, enter the momentum values of each individual cart and of the system of the two carts before and after the collision. So let's go ahead and do this. The red cart was 0.5 kg, moving with a speed of 60 centimeters per second. Let's go ahead and multiply mass times velocity. 0.5 times 60. There we go. So before the collision, the red cart has a momentum of 30. A 1 kilogram blue cart, speed of 30. Okay, so before the collision, because it's left, the blue cart has a -30 momentum. Okay, so what is the total momentum of the system before the collision? Well, these are the MV. When I combine them, it's 0. Now, what did I say? I said that the total momentum before and after has to be 0. So that means after the collision, it's got to be 0. Let's see if it is. After the collision, the red car moves leftward. So now the red car is moving left with a speed of 40. The red car had a mass of 50 and a speed of 40. So this is going to be -20. The blue car moves rightward with a speed of 20. Okay, so the blue car is going to move rightward with a speed of 20. So right is positive. 20 times 1 is +20. Oh, when I add the momentum after, it equals 0, but I already knew that. So when it said momentum change, this is delta P, this is impulse. How did the momentum change for the red car? The momentum change went -50. 30 and -20 is -50. But now when you go, think about it as a number line. If you're going from 30 to negative 20, you're moving 50 spaces in the number line and you're going left. But now think of the number line. You're starting at negative 30, you're going to positive 20. You're going 50 spaces to the right. And again, the total momentum of the system remains the same. That is the key. So I just wanted to explain how to do this problem so that we were all on the same page with that. This is an example of a totally elastic collision. A totally elastic collision is where two objects will bounce, but all momentum is transferred entirely from one to the other. So that means when you start, only one object is moving, and when you end, only the other object is moving. So essentially, let's think about it. We know this is the general equation for elastic collisions. But I said if you have a totally elastic collision, you start off only one object is moving. So that means the velocity for the other object is 0, which means this whole thing cancels out. And if this one started off moving, that means it ends up at 0. So that means this one goes away because of 0. So this is just a simplified form of using the totally elastic equation. Okay, you could still use the original elastic equation, but this is just like a shortcut. So if I'm going to use the shortcut, I have a bowling ball and I have a bocce ball. So if I have a 15 kilogram bowling ball that rolls 3 meters per second, collides with a 9 kilogram bocce ball totally elastically. So I know that because it was totally elastic, the bowling ball was moving before the bocce ball started at rest. They collide, and the bowling ball ends up not moving, and then the bocce ball ends up moving. Simple. And that makes logical sense. The object with more mass moves slower than the object with less mass. Just algebra. Okay. This is an inelastic collision. So elastic, I think elastics are bouncy. So things that are elastic tend to bounce. If things are inelastic, what they do is they collide and they stick together. And I found this really awesome animation here. It shows these two carts sliding, and the vertical lines are the momenta of each one. So you see the one on the left, the red, starts with a bunch of momenta, and what happens is it loses some when it hits the other car. Then the other car gains the momentum that it lost because the momentum was transferred. They both move slower, but then they move as one object. So the equation that we're going to use for inelastic collisions, or things that stick together, the momentum of the first object plus the momentum of the second object, and because when they collide they stick together, you only have one object moving after the collision. So you only have one thing moving after the collision, so you're going to add up their masses and then do V prime. So this is really important. Inelastic collisions could be car accidents, they could be you run into someone and you tackle them. You guys are separate, and then when you start tackling each other, you combine and then you move as one object to the ground. Okay, this is a very common and practical thing, but they must obey the law of conservation of momentum. So let's see how this works. Here's another little GIF of it. I have the two objects going towards each other, but the one with more mass wins the collision. They bind, they're like magnets, and then they move in the direction that the larger one was going. That's very logic, common sense. Now, let's look at this problem. Little Susie has a mass of 40 kilograms, is running down the hallway at 3 meters per second. She collides with Nellie Newton, who has a mass of 50 kilograms, who is walking -1 meters per second inelastically. So because it says inelastically, they stuck together and fell down to the floor. How fast do both of them move together after the collision? Well, because it says inelastic, I'm going to use the inelastic equation. My first person will be little Susie. My second person will be Nellie Newton. And then my last object would be them moving together. mass times velocity of little Susie, mass times velocity of Nellie Newton, and then what I do is I add their masses to get the mass of both of them together. And this makes sense. If they were running towards each other and they're approximately the same mass, they're not going to move incredibly fast in one direction or another. This is an inelastic collision. So the other form of problem that I'm going to give you is inelastic collisions. So let's go ahead and take a look at this. A 50 kilogram red car, or 0.5 red car, is moving right with a speed of 60. So again, all we want is momenta. So before the collision, this is really simple. It's going to be very similar. 0.5 times 60 is 30. When it collides with a 1.5 kilogram blue car that is moving leftward with a speed of 12. So this is going to be negative. Where is that? This is going to be negative 18. Please pay attention to right and left and the negative and positive signs. That will mess people up. After the collision, the two cars stick together and move to the right with a speed of 6. Okay, so I know that after the collision, the red car was 50. After the collision, how fast is the red car going? The red car is going 6 because it's moving the same speed as the blue car. They're both going 6. So after the collision, what's the momentum of the red car? It had a mass of 0.5. It had a velocity of 6. So and this is right. So after the collision is going to be positive 3. After the collision for the blue car, 1.5 times 6 is going to be positive 9. 1.5 times 6. Okay? I know I'm doing it a little differently this time, but again, tricks. When I add positive 30 and negative 18, I get a positive 12 momentum. This number doesn't have to be 0. But when I get this number, I know that this number has to be throughout because it never changes. So I know this had to be positive 12. Positive 30, positive 9 is positive 12. So I'm just checking my work in another way. Now, what is my momentum change going to be? Let's find out. If you're going from positive 30 to positive 3, that is a negative 27. Final minus initial. Science is always final minus initial, after minus before. What is 9 minus negative 18? Positive 27. So this is key, and I think I may not have been as clear on the other one as I should have been. The momentum change is always going to be 0. The momentum of the system is always going to be the same. Because the law of conservation of momentum says that the total momentum never changes. It just is transferred between objects. So I don't care what that momentum is, I just know it never has to change. The total never changes. But you can have momentum. All I know is that you're going to have the same before as the same after. So pay attention to how this works and understand that momentum is conserved. Because momentum is conserved, that must always be 0. So I know this isn't the easiest stuff ever. I do. But I know you can do it. Take some time, watch this a couple times, go Google some things that you're confused about, ask me questions. This is important physics stuff that I need you to be exposed to before you go to college. I know I know I know we're hitting the point of frustration of like, why are we doing this? This is important in terms of physics and understanding what physics is really about. You need to understand what momenta and what collisions essentially are. So ask me questions if you have them. I have office hours every day from 12:30 to 1:30. And even if you don't need help, come by, say hi. It'd be great to catch up with you guys. Hope all is well, and I will catch you guys next time.